It's a nice image. Yeah, I like that reaction. Yeah. So this image is actually taken from an amateur astronomer. I think his name, I think maybe he's from Chile. This was taken in Chile, I think. And what you're seeing there is just, this is, the Earth, and then I think he's somewhere near a pond or something, and this is a panoramic view. And what you're seeing is the Milky Way. This is our home, right? This is where we live. That big patch of sky with bright spots and dark spots, that's our home. We're part of this cosmic structure. The stuff you see that's dark there is actually dust between us and the star that we're observing. And the dust actually obscures the light. So the stuff we don't see is hidden in the dust. And the dust is actually processed material from stars. It's like volcanic ashes. You can imagine that, right? This is the same thing that the stars are doing. Stars are blowing up stuff, and it's filling up the galaxy. My talk today is not really going to be about the dust. It's going to be about the rest of it, so the stars, and what we call dark matter, which is holding all this structure together. So this is a really nice image. So if you had a $1,000 camera, you could take something like this. How many of you are amateur astronomers in here? Yes. Yeah, so you could do something like this, right? If you have $100 million, you can build a spacecraft like the Europeans did. This is called a Gaia spacecraft. And you can send it to space, and then you can take this kind of map. To us astronomers, this is way more impressive than the thing I just showed you before. This is a map of stars in the Milky Way, and we can actually see both the northern hemisphere and the southern hemisphere, because you're in space, you can just rotate around and take all the pictures. Versus when you're here, you're only sensitive to your hemisphere. You can see things, in the southern hemisphere, for instance, if you're in the south. If you're in the north, and you can see the things in the northern hemisphere in the south. So what you see here, these are star count maps. So the plane of the Milky Way is still here. So you see a bunch of stars that are obscured by dust in a very interesting pattern. And then you see, sorry, let me start my timer. And then you see two bright spots here. These are actually our satellite galaxies. They're called the Large and the Small Magellanic Clouds. They're named after Magellan, who was an explorer. Some of you know this guy. So these are satellite galaxies that are orbiting the Milky Way. And then I think you can also see maybe some bright spots there that are clusters. We tend to divide the Milky Way into some structures. So we live in what we call the disk, which is made of mostly young stars. When I say young in astronomy, this is 8 billion years old, so 0 to 8 billion years old. So that includes stars that are being born up to 8 billion years old. And then the halo is this structure that has much older stars, and these are maybe 10 billion years old. That's very old. And then the satellite galaxies are labeled here. And then the bulge here is really you're looking toward the galactic center. And if you want to have a perspective, we're around here, and we're looking towards the galactic center. We're not in this map, right? We're taking the image. OK, any questions so far? All right, yeah.
Wait, we're not in the map? What does that mean?
Well, we're taking this map, so we can be in it, right? We're taking an image of the stars. Okay. Yeah. But we are, if you were to put us, we'll be like around 8 kiloparsec, which is a unit that astronomers like to use. So a parsec is like 3 light years. Light would take like 3 years to get to us if it was if you had like a star at a parsec. So we are around 8 kiloparsec from the galactic center if you want to situate yourself. To the galactic plane, yeah. So we are actually pretty in the disk. We are around 23 parsec. So I say we're 8 kiloparsec. That's 8,000 parsec away from the galactic center, and we're a little bit 8 kiloparsec above. So we are, if we're a star, I will put us like around here. Okay. This is just a, again, we're not in this map. Just think of it as a 3D structure. Does that make sense? Okay. All right. So this is our home. So we not only can we measure positions of stars, we can actually measure the motions of stars. So this is called proper motion. So when you take an image of a star, this is binary star, and then you come back next year, you take an image. Stars that are moving so fast like this one will actually change position. You see that most of the stars in the foreground are not changing. Then you can measure the motion of these stars. So we usually measure this in arc seconds. So a second of an arc is an angle per year. So this one is actually very fast. It's 10 arc seconds per year. With Gaia, now this is going to be impressive. We can actually map simultaneously motions of billions of stars. And what you're seeing here is not all of them. This is just a few stars that are within 100 parsec. And if you forward integrate their motion in time, this is what you see. Stars actually move on time scales much longer than our lifetime. So this is actually just forward integrating their motions in time. But we can measure them. They're very tiny, but they're not this dramatic. So what do these patterns that we see in a galaxy teach us about its formation and its evolution? So to do that, I'm going to start from the beginning, which is this. What you're seeing here is the oldest light, or the farthest light that we can see as astronomers in a galaxy. It's called a cosmic microwave background because it's a background of light that we usually see in the microwave region of the electromagnetic spectrum. And what you're seeing here are temperature fluctuations. So usually this map is pretty homogeneous at around 2 Kelvin. But then what you're seeing here is 1 part in 25,000. So these very tiny fluctuations that astronomers have been able to map very precisely. And this is the oldest light in the galaxy, and we think this comes from the Big Bang, maybe 400,000 years after the Big Bang. And from this, we think that's where all the structures form. So to form structure, like our galaxy, planets, asteroids, right, you need to start from something like this, and then add some other ingredients, which I will talk about in this talk, mostly dark matter, and what we call dark energy. And then you can actually reproduce what we see. And this model is called a lambda CDM. Lambda is a funny word. It just means the cosmological constant. And CDM here means cold dark matter. So if you take cold dark matter in this map, and you take dark energy, you evolve that in time, you can actually form structures in the computer, in a simulation, that resemble what we see today. So a little bit of history. So what we're seeing is light around here, 300 or 400,000 years before, after the Big Bang. We are here at 13 billion years old. Most of the stuff we see here, so what James Webb, if some of you have heard of James Webb telescope, maybe? The James Webb telescope is trying to look for lights that around here, like first stars and first galaxies. So I've talked to you about like the initial structure that we start with, and then I told you that we're going to add dark matter, and then we're going to add dark energy. I'm not going to talk a lot about dark energy, but this is probably going to be about dark matter. So dark matter, after this talk, I will probably have convinced you why we think it exists. But what I'm showing here as a slide is just what dark matter is made of. So we think dark matter is a particle. If none of these terms make sense to you, that's fine. I'm just putting them out here. So when you see this term on YouTube from Neil deGrasse Tyson or someone, that term can make sense to you. So what you're seeing on the x-axis is the mass of dark matter, which is measured in electron volt. We know that energy and mass are equivalent, so we're just using that. And then, so it ranges from very tiny. You can see the orders of magnitude here. We're going from 10 to the minus 21 to 10 to the minus 30. This just encompasses a lot of uncertainty. We don't really know what it is. So we have so many candidates that we're still searching. And when I label here something like wave-like versus particle-like, it's just a way to say that if you have a very small particle, it starts becoming like a wave. Versus if you have a very large particle, you can use particle to actually talk about that. So this is the mysteries of quantum mechanics. So we know from quantum mechanics that if you have, let's say, a photon, the photon is so light that you can think of it as a wave. But if you have, let's say, a proton, which is a much more massive particles, you can think of it as more of a particle. But wave and particle are interchangeable. What I want you to take from this slide is that we have a lot of theories, a lot of models of what we think dark matter should be, but we think it's probably a particle. So how do we go from the map that I showed you of the cosmic microwave background, we add dark matter, to what we see today? So what I'm going to show you is a simulation of dark matter structure as we will see today in a galaxy. And this is from some simulations that were run at Stanford. So what you're seeing here, we're kind of just working through this cosmic web. You can think of our galaxy as one of these little structures here. You can observe, what you observe here is that you see big structures, so those are probably classes of galaxies that are forming and merging together. And then you can see clumps at all scales, right? You have very tiny clumps, very big clumps, and you also see like feeding networks where galaxies are kind of feeding into each other through these networks, like it's a web. So this is where we think galaxies form. So for instance, let's go to the next slide. So you would take like this small structure and put a galaxy there, if you're doing a simulation. So what this looks in practice, these are simulations from the Auriga team, which is based in the UK, is you have that cosmic web of dark matter that I was showing you before that's assembling, and here we're zooming in on a Milky Way-sized galaxy. And then you have gas that's falling into that dark matter. This is mostly hydrogen, and as it's falling into the dark matter potential well, it's starting to form stars, which you're seeing here. And you're forming a tiny little galaxy with spiral arms, like our galaxy. And then you have satellite galaxies that I showed you. If you remember, I told you about the small and the large Magellan clouds. Some of them are like zooming in. You see that little thing zooming in and being merged with our own galaxy. So this is how we think galaxies form. And these models work pretty well. There are things that they don't explain. For instance, what is actually dark matter? Right? We still haven't told you, what we think it is. I just gave you a bunch of possibilities, but what is it? Is it one of those particles? Which one? We pretty much understand how gases work, right? We understand how we work on Earth. We have gases, we have fluid dynamics, so we can probably model this pretty correctly. And we can understand how stars work. So the mystery of dark matter. So we think dark matter clumps at all scales, as I showed you in the previous video that was zooming around. But the amount of clumping, so how many clumps you have, depends on what dark matter is made of. So if you have, let's say, what we call cold dark matter, which is CDM, which is made of mostly WIMPs, so these are weakly interacting massive particles, versus if you have what we call self-interacting dark matter. So in cold dark matter, you have these particles that don't interact with each other. But if you have particles that interact with each other, you get a different structure. And if you have warm dark matter, which is a different model, it could be neutrinos or something. But there are many models that, it's not just these three. People have cooked like a million models. But the idea is that you get a different level of clumping of substructure depending on what you assume for a Milky Way. This is like a Milky Way size halo around it. So this is 100 kiloparsec, and the Milky Way is around 300 kiloparsec in size. So how do we test these models that have different predictions on the level of clumping that we see in the galaxy? Let me check my time again, sorry. So to do that, I'm going to take you on a very small tour of why we think dark matter exists. That will not just speculating forever. So starting with this picture, this is Dr. Vera Rubin, who's an astronomer in the 70s. She made these important measurements that started this field. This is, I think, her image at Lower Observatory in Arizona. Have any of you been to this observatory before? Oh, we have some people that are interested in this, yeah. So Vera Rubin is here, and she's the one who made the first measurements of this, of dark matter. So the measurements she made, this is not her paper, but this is just to illustrate that. It's called galaxy rotation curves. So stars and gas in a galaxy rotate in a disk, as I showed you in those images. So what you have here is distance from the center of a galaxy to the outskirts of the galaxy. And on the y-axis, you have the velocity in kilometers per second. If you don't have dark matter, this is the rotation curve that you expect. So it rises up and then it falls down as you have less matter on the outskirts. But what we see is actually that the rotation curve is mostly fairly flat. So you can say, okay, this makes sense. It agrees with this, what we expect here. But then what's happening around 30,000 light years, right? Why are stars moving faster there and gas moving faster than we expect? Well, you can say, okay, gravity is broken down at larger distances. So some of you have heard of the term modified gravity. So people are taking Newton's laws of motion that some people learn in high school, and they're just changing them at larger distances. That's one way to do it. The other way that we like is just invoking extra mass. So there's some extra stuff there, but we can't see it, and we're going to call it dark matter. People don't really like that, but that's a solution. And then you can say, okay, how much stuff should there be? Just as much stuff I need to reproduce the rotation curves. That's one evidence. That's one reason we think these things exist. Another evidence of this is called gravitational lensing. Now, this concept here, this is a conceptual diagram. It's not really data. But the idea is that you have light coming from, let's say, a galaxy, and then you have stuff between us and the galaxy. So maybe a galaxy cluster that's very massive. And then as light propagates from the galaxy to us, it gets bent, lens, just like in my glasses. It's not the same phenomenon, but the idea is that what we know from Einstein is that if you have a lot of mass, you will bend space-time, and then you're just changing how light propagates from us to that galaxy. So that's what this is illustrating. And another illustration that I'm going to show you is this. This is, I think, from Robert Hurt, who's at JPL in Caltech. He made this illustration where, let's say you have an image of a field of galaxies, and then you can add dark matter. Look how creepy that becomes. So the light is being bent, so you're seeing this very distorted shape. But you can't see the dark matter, right? That's between us and the galaxy. So you're just seeing this distorted shape. This is an animation. This is data. This is an actual image from the James Webb Telescope. It was one of the first images that were released. And what you're seeing in this image, you're seeing a lot of things. So each one of these spikes here is a star, and one of the fuzzier blobs are galaxies. And then you see these arcs here, and this, it's not an unfocused image, it's very focused. But you're seeing this very distorted shape. And we think it's just lensing. And then you can say, okay, we can explain lensing without actually invoking dark matter. Let's just say there's a lot of, but you need a lot of mass, basically, to get the shape to match. So people invoke dark matter, models do this. And these images were actually showed to Joe Biden at the press conference. I forgot which date this was. This was the first releases of JWST. So other observations here include galaxy clusters. So what you're seeing here is a cluster of galaxies. That's what you're seeing here as as light. And then what is the blue stuff, right? That's the first thing that comes to mind. So the blue stuff are X-ray. It's light in the X-ray region of the electromagnetic spectrum. And the reason we think this has something to do with dark matter is that this light in X-ray is emitted by gas that's around this galaxy. So as gas falls in this dark matter potential, it gets heated, and it emits this light that we see here in X-ray. But what do you notice, right? You see that the shape of the X-ray, so the shape of this blue light, doesn't always, right? It doesn't always follow the shape of the galaxies that you're seeing, right? For instance, you're seeing, let's say you're seeing a lot of stuff here. I can't touch it, but there isn't a lot of galaxies there, a lot of visible matter. Then you can invoke dark matter. You say, okay, there is extra mass there that can actually explain all these shapes that I'm seeing. Or you can try to change gravity, which is harder. Another evidence of, this is really not, let's call it evidence, but the idea, you've seen the simulations that I showed you where you see galaxies clustering at all scales. This is actually data. This is just if you take the galaxies that you observe at a certain angle, and then redshift here just is a proxy for distance. So the smaller number means it's closer to us versus it's further away from us. You see this structure in the map of galaxies that actually matches what we observe in simulations with dark matter. So all this evidence that I've showed you make us think there's something such as dark matter. Okay, I'm going to stop here first and maybe take some questions before I move on to the next section. Yeah.
I'm a little confused about this.
Okay. This does not prove dark matter. What this picture is showing is it's showing you that the cluster of galaxies that we observe, maybe this is not a good image, it kind of matches. And to actually explain it, you need to invoke something like a dark matter model and also invoke something like a cosmological expansion. Otherwise, you have a really hard time trying to reproduce the structures that you see here. But it's not, a smoking gun for dark matter. If we had that, I wouldn't be giving you this talk. We're still trying to figure out what dark matter is and if it's actually there. Yes?
What percent of the universe or galaxies is actually visible matter compared to dark matter? I think it's very impressive that we don't really see very much of it.
Yeah. If I remember, it's like 4% of the matter that we see is visible matter of the universe, right? Yeah, and like 20% in dark matter, and then the rest is dark energy. So yeah, it's a very tiny fraction in terms of mass.
So why haven't we been able to find any dark matter particles?
That's a good question. So there are many reasons. So people are searching. Let me maybe bring back that picture here. And they're ruling out some of the parameter space. This is not this is just one parameter, but there are multiple parameter spaces that people are ruling out. But we haven't actually found an actual convincing. For instance, it depends on what's actually the dark matter density here on Earth, because we're doing experiments on Earth. This is how people usually do that at SLAC. Where I'm based. So they usually either smash particles into each other, trying to see if what you see makes sense, or if you need to invoke dark matter. There are many ways to do this, but it depends on what the actual dark matter, the local dark matter density is. So that is probably low. But in terms of mass, as you see in the simulations, a lot of mass, just seeing like the scale of the structure, which is dark matter, compared to like the actual galaxies that we see, you can see that it's a much tinier fraction. Okay, so the last evidence here, which is not really evidence, it's these really nice images. These are dwarf galaxies. Dwarf galaxies are, as the word says, these are tiny galaxies. In astronomy, we like to say dwarfs and giants. So we have dwarf galaxies, we have giant stars, we have dwarf stars. But these are tiny galaxies that are very close to us. That's why they're so, we can photograph them since they're so faint and tiny. But to explain the abundance is basically how many of them should be around the Milky Way-like galaxy, and to explain their shapes and their properties, like how much metal there is, how stars rotate in these galaxies, you need to invoke something like dark matter. Okay, now let's go back to our Milky Way, and let's see what the Milky Way can teach us about. So we're going from large-scale structure, different galaxies, galaxy clusters, to the Milky Way. Let's go back to our home Milky Way that I showed you in the beginning, and see what this can teach us about the structure of dark matter. So one interesting thing that happened in the history of Milky Way is called the Gaia sausage. Now, this is a funny name, but it looks like a sausage. So what you're seeing here is the radial motion of stars, so how stars are moving radially, how much they are, this is in kilometers per second, versus circular motion, how they're moving around the galaxy. And that's also measured in kilometers per second. The galactic disk is just a bunch of stars that are moving circularly, that are centered around zero radial motion, so the galactic disk is not, being tugged away from the center of the galaxy. It's there, but stars are moving rotationally around it, so that's the dark spot. And then you have this extended structure that's formed what we call the galactic halo, which I showed you in the beginning, so this extended structure around us. And most of the stars in the galactic halo have a different motion compared to the stars in the disk. And it's mostly circular, and it's in this sausage structure. Now, how do you form this kind of thing? This is the data. This is what we see. Again, because I told you we have this telescope that can measure precise motions for billions of stars. So if you just plot how they're moving radially versus circularly, you get this image here. So how do you form this structure? So here's a simulation. So in astronomy, we like to do simulations because things are interactable. If you have a billion particles, right, you can just write that on a piece of paper and figure it out. People do that analytically, but we like to run simulations. So what you're seeing here is the formation of the Milky Way halo. So how do you get this thing? Like a sausage structure in the galaxy, you have a proto-Milky Way, so a young Milky Way, and then you have a dwarf galaxy. A small galaxy that's in the cosmic void, not void, but the cosmic wave that's kind of smashing into us. But it's merging with us radially, that it's depositing debris around the Milky Way disk that are just moving radially. So you see this thing here in orange or red. That what explains the formation of the galaxy. And this galaxy itself has its own dark matter. And then you can ask yourself, what happens, when you have a dwarf galaxy like Gaia Enceladus or Gaia sausage merged with a Milky Way-like structure. So the bottom line is we still don't understand, that's one thing. This model, even though it's kind of the standard understanding right now of the formation of the Milky Way, there's still some debates actually if this happened. So there are people who propose that you can actually form this kind of structure, like the Gaia sausage, by just secular motions of stars as a function of time. So there are still mysteries in our own galaxy. Again, I'm going to bring back this image or these simulations that tells you that galaxies form in these dark matter structures, and big galaxies formed by eating smaller galaxies. So you have a dark matter structure, you have the gas, and then you have the stars. And then the question you can ask yourself is, how many little, tiny little dwarf galaxies should be visible in a Milky Way-like structure? For instance, What do you notice about this frame and this frame? Besides the fact that, okay, maybe I'm not going to tell you the answer. What do you notice here between dark matter and stellar light? Way more particle in the dark matter than in the stellar light here, right? Why is that? Right, they're not visible, obviously, because they're not there. But why?
Oh.
Right. So that's an interesting question, right? We're trying to understand why do we have so much stuff in our simulations compared to what we actually see in stellar light? And the answer is that these small dark matter clumps don't have enough gravitational potential to attract a lot of gas to actually form stars. But the question is how much, basically how many of them should there be in a Milky Way-like structure? Basically how many of them don't have enough mass to attract the gas to form stars? In other words, what is the mass spectrum, what is the mass distribution of dark matter clumps in a typical Milky Way-like halo? And that will change depending on what you assume the dark matter is made of. So if you assume the dark matter is made of weakly interacting massive particles, you get a different answer. If you assume the dark matter is made of what we call the axions, or if you assume it's stereo neutrinos, you get a different answers. But we can test that directly because we're in the Milky Way. We can just count how many satellites we get there, right? Yeah, sorry, go ahead.
Tell us more about the gravitational the potential.
Yeah, so maybe I use the word potential. So basically just how much gravitational pull does a small dark matter clump have, right? That tells you how much gas it retains, and that tells you how many stars form in it. So if you have just think of it as a cup of water. If you have a very small cup of water, you get less stuff than if you have a very big cup of water. Right? So that's the same concept here. As these small particles are smashing into each other, the gas is kind of falling into this dark matter potential, and it's forming stars. The question is what is the spectrum? What is the distribution of these dark matter halos around the Milky Way like? And that will depend, again, on the dark matter that you assume. So in the Milky Way, we have these tiny little clumps here, which are our satellite galaxies. Again, remember I told you about the small Magellanic Cloud and the large Magellanic Cloud that are named after Magellan, the explorer. And we have actually tinier ones that you couldn't see in the first image, but if you zoom in, they're like this one. There's Sculptor, there's Fornax, there's Carina, there's the Leos, Sextans, Draco. These are all small, tiny galaxies that are kind of moving around us. And we think they form from a small dark matter clumps that just had enough gas to form stars. The ones that didn't have enough gas to form stars are not visible. Then you can ask, how do you see those? And that question will be answered, at least partially, after this talk. So, but the takeaway here is that we still don't understand how many of them should be in a typical Milky Way-like galaxy. So I'm going to tell you about a new probe that is going to help us answer this question. And this is stellar streams. So what is a stellar stream? It's this structure here. So what you're seeing here is the map of the northern sky. This is actually in New Mexico at, I think Apache Point, I believe, yeah, Apache Point in New Mexico. And this is a 3-meter telescope. It's 3.5 meters, so it's a little bit bigger than the Shane. And what this telescope does is just taking images of the sky that are deep. And the dark spots here are places where they didn't take any images. But what I want you to pay attention to are these streaks of stars that are named. For instance, this one that's named Palomar 5 was discovered in Palomar. There's this one, it's called GD1. I forgot actually what GD stands for. There's this one, it's called Orphan. And then there's this big streak that we call Sagittarius stream. These streams here are probably going to be the next biggest thing in astronomy because they may help us answer the big mysteries about dark matter. We actually have lots of them now with Gaia, that amazing telescope that can map motions of stars. One thing I forgot to tell you is that not only are these things clumps, right? They're not just clumps of stars, like streaks that you see here, but all these stars actually in each clump are moving together, which is super amazing, right? So you have a bunch of stars that are clumped together in the stream and they're just moving together, versus everything else is just moving randomly, right? That's exciting. That's interesting. So some of these were found in the 90s, and people were like, what is this? So now we have a lot of them with Gaia that can map. We have around 100 of them. Some of them, you can see they have different morphologies. Some of them are thin, some of them are thick. Some of them only have a few stars. And we actually see them in external galaxies. This is not the Milky Way. So now you're just taking an image of a galaxy. I think some of these were taken actually by amateur astronomers. So if you just take a deep exposure of a distant galaxy, you will see these features around it. You see these like dark features. So the galaxy here is at the center, and then you see a bunch of dark features around it. And then you also see, these are just stars in the foreground. These are super interesting. How do you get structures like this, right? Does anyone know? Dark matter. Okay, dark matter is the answer, but not quite. Right? Dark matter is part of the answer. But what you're seeing here are just disruptions of galaxies as they're merging into each other. So I have some simulations here, which are from Jason Hunt in New York. So you have so what you see there is the dark matter. This is gas, and then you have stars as well. So stars, dark matter, and gas. And just different orientation in different galaxies. But the point is you have this small galaxy, a little bit smaller than the parent galaxy, that's kind of merging and depositing debris around the parent galaxy, right? So then you get features like this. If you were just to take a snapshot of this simulation, right, you would get something like this. Does everyone agree with this? That if you just stop the simulation at some point, right, you will get streaks around galaxies. And this is actually data. This is simulation. All right. So this is one type of stream. So that could explain something like Sagittarius, this huge streak that's we can observe in the northern hemisphere. But what about the tiny ones, right? So you can see that all these streaks here are especially thick, right? They're not very tiny structures like this one. Like you see tiny structures, but let's say Palomar 5. This is a very tiny structure. How do you form those? Well, the answer is you actually have, instead of galaxies that are merging into each other, you have clusters that are just being tidally disrupted by the forces of gravity in the galaxy. So I'm just showing some really nice clusters here. These are called globular clusters. They're old. For instance, this one is 3.5 billion years old. This one is 8 billion years old. This one is 12 billion years old. And what happens if this thing is moving in a galaxy? So this is an animation that I made. It's very bad, but this is kind of the concept. So you have a cluster of stars. And as that cluster is moving around the galaxy, stars get slowly ejected out of that cluster. And they form streaks that you can see that are less extended than something like a dwarf galaxy that's merging into us. It's the same concept. It's just gravity kind of disrupting either a large cluster or a small cluster. This is, again, I'm bringing back Palomar 5. This is a much nicer image of it. It's kind of cleaned up, so we removed stuff around Palomar 5, and this is just Palomar 5. Again, remember, these stars are all moving together, which is super cool. So everything in this streak is moving together. Everything in the background is just random motions. What do you notice about this image? The bright spot in the middle, that's one thing, right? Okay, that's one. What else? There's a kink in that track, right? There is, are you talking about like you have this arm and then that arm? Yeah, okay. All Right, so this is the central cluster that's being pulled away as it's moving in a galaxy. So you have like a leading arm and a trailing arm. Okay, what else? There's a missing portion in the bottom left. So, all right, this one is like, this arm is a little bit short. Oh, sorry. Oh, this? Ah, okay, all right, that is true. This is just, they didn't take data there because there's no stream. We're just focusing on the stream. Okay, maybe I say something else. There's, yeah, this arm is a little bit shorter than that arm, okay. But what else? One more interesting thing. Yes! Okay, yes, that and this part here. Do you see that? So you see that the density kind of drops and then picks back up again. Do you believe me? Yeah. Okay, all right. So this is actually very interesting to us because we think it's actually dark matter that we can't see. Remember I told you that you can have these dark matter clumps that are not massive enough to actually retain gas and form stars. What happens when you have that dark matter clump interact with this cluster? I made a very tiny animation here where you have this cluster. This is just three different positions. So this is x, y, x, z, and y, z. So this is 3D coordinates. But do you see what happens to the cluster? It gets disrupted by a dark matter clump that doesn't have any stars. So remember I told you we want to actually count how many of these small clumps don't have dark matter, because that actually that don't have stars, because that actually tells us what dark matter is made of, because it depends on the particle nature of dark matter. So this is one of the promising ways we may be able to actually detect dark matter, by seeing its gravitational effects in these tiny little streams that we see in the Milky Way. Again, this is super interesting, at least to me. This is kind of what I'm kind of focusing on now, my postdoc work on, which not what I did in my PhD. So it's kind of like this, right? This is like an analogy where you have this actually was taken a few days ago somewhere by Tom, I think during one of the holidays, where you have, let's say a plane or something, you get like this dark spots here. It's not exactly the same process, but this is similar. So you can infer that there's something disturbed this stream structure. And for us, everything is dark matter. Okay, all right. So not only do we see that in Palomar 5, now I'm actually showing you real scientific data. We actually see some weird kinks in GD1 as well. So you see at minus 70, you see that weird kink. You see something at minus 20 in GD1. You see, so some of these clusters retain their parent cluster, like Palomar 5 still has that central cluster, but GD1 doesn't because it kind of evaporated. And then you see this too in, this is called the orphan chain upstream. So all these structures we think are caused by dark matter. But there's a caveat, it might be caused actually by black holes or anything else, but we're just going with dark matter for now. All right. So now we have around a few of them in the Milky Way, so around 20, but we think there should actually be more. If you want to know more about this, you can ask me later. So just in the last few minutes, I think I have 4 minutes until 45. So I want to tell you about the next telescopes that I'm excited about that are actually going to help us solve this dark matter problem with streams. So some of them are here. So starting with the Euclid telescope, which was launched in July by Europeans. This telescope operates around 1.5 to 2 micron, so between optical and infrared. And then there's the Verubin Observatory, which is really an American project. It's mostly built by Americans, but it's going to be running in Chile, because it's really nice dark sky in Chile. This is the largest camera that have ever been built by humans. And then there's the Nancy Grace Roman telescope. This is going to be a space telescope. So these two are space telescopes. This one is on the ground. It's actually just taking deep images of the sky in Chile. So Euclid has actually started releasing data. And wow, this is amazing. No streams yet, but this is just images of different galaxies. It has a much better resolution than, let's say, Hubble. And this is just, I'm just kind of showing more images of Euclid. So what you're seeing here, it's a galaxy cluster. And then you can zoom in, see tiny galaxies that are, that I've told you about. Those are called dwarf galaxies. And these are, again, tiny dark matter clumps. And then inside those dwarf galaxies, there is actually clusters of stars, like globular clusters. And those globular clusters may actually even disrupt and form streams. But Euclid haven't actually shown any of that. But you can see that its capability is way above what we can do with current telescopes. And then the Verubin Observatory, again, I just told you that this is the largest camera ever built by humans. But what's cool about this is it's going to take an image of the sky every 3 days for the next 10 years. Imagine how much data that is. So it's going to make our job much harder. You have to go through that data and do a lot of data analysis, which is boring. But at the end, you might actually, so the reason this is exciting is we're in the business of measuring motions of stars, right? That's really what matters to us, is how stars move. Because everything I showed you before in those movies, it's stars moving, bumping into each other, doing all this kind of forming all these kind of interesting structures. And having a camera that can do that for the next 10 years is amazing. So we're going to be able to measure motions of stars very precisely. And then the next Instrument telescope, which is different from these two, it's a space telescope. But the cool thing about this telescope is it's going to take images that are much bigger than any image you've ever taken with, let's say, Hubble. So one Hubble image, I don't know how many of you have seen a Hubble image before? All right. One Hubble image, one Roman image is 400 Hubble images. So whatever Hubble was able to do, this one will be able to do it much faster, 400 times faster, and much deeper. So in a paper that I wrote with Sarah Pearson and others, we showed that if you were to look in Andromeda, which is our closest galaxy, this is simulations, you should be able to actually see streams in Andromeda. So these tiny clumps of stars are being disrupted, which is what I'm showing here. And you should be able to see gaps in them from dark matter halos. Although, we don't usually do our analysis by eye, so if you don't see the gap, that's fine. We have tools that can actually detect underdensity and overdensities in these streams. And if we count how many gaps we see in these streams, we should be able to actually constrain the nature of dark matter, because that tells us how many little clumps of dark matter didn't actually form stars. So they're just moving around, messing up streams and forming these underdensities. Okay, so I'm going to stop there and give you a summary. We think in astronomy that galaxies form in halos of dark matter. And we think dark matter is real because it can explain a lot of hypotheses that we see, like how galaxies clusters, how things move in the universe. But you can also reproduce the same kind of behavior with modified gravity, which I didn't spend time on. And then we think the Milky Way, our home Milky Way, is actually a nice, excellent probe. We'll discover a bunch of streams, and we want to actually understand the nature of our satellites. That actually help us put constraints on the nature of dark matter. And then we have new tools, new telescopes that are going to actually help us answer these questions. So I'm very hopeful. In 10 years, I'll come back here and tell you we know what dark matter is. All right.